Welcome to the new era of video creation with VAEs 8. Today we will discuss with video generation. Here is our contents. In recent years, the field of video generation has experienced significant advancements due to breakthroughs in artificial intelligence, particularly deep learning. AI models are increasingly able to create compelling, realistic video content from scratch or with minimal input from users. The most common approaches in this field rely on models such as GANs, VAEs, and RNNs, which enable machines to understand both spatial and temporal data, which are crucial for creating realistic videos. These advancements have a profound impact on various industries, including entertainment, where AI can be used for virtual actors or digital effects, and in education and healthcare, where AI can simulate complex procedures for training. Ultimately, the goal is not just to generate videos, but to generate them in a way that feels natural, consistent, and lifelike, approaching or even surpassing human-created content in quality and efficiency. This growing capability to synthesize video is opening up a wide range of potential applications that can revolutionize how we create and consume media. Video generation, as a field of AI, has evolved from earlier work in still image synthesis. Initially, AI focused on creating high-quality static images through techniques like GANs. These models excelled in producing realistic stills, but video poses an additional challenge, incorporating motion and maintaining temporal consistency. Early video generation efforts often faced issues with maintaining coherent motion over time, and models that worked well for still images were not directly applicable to video due to the need for frame-to-frame continuity. For instance, a video consists of a sequence of frames, where each frame needs to smoothly transition to the next, requiring the model to not only understand the spatial relationships in each frame, but also how these relationships evolve over time. The introduction of models like LSTMs, which were designed for sequence data, helped address some of these temporal challenges, and since then, the field has expanded rapidly to include more sophisticated methods, such as 3D convolutions and transformers, which further improve the consistency and realism of generated videos. Several key technologies form the backbone of modern video generation. The most notable among these are GANs, which consist of two competing networks, the generator and the discriminator. These networks work together to generate content that is indistinguishable from real data, and GANs have shown great promise in generating highly realistic videos, even from random noise. Another important technology is the variational autoencoder, VAE, which learns a latent representation of the data and can generate new content by sampling from this latent space. While GANs are known for producing high-quality images, VAEs are often more stable during training and can be used to generate diverse video content. When it comes to handling the sequential nature of videos, recurrent neural networks, RNNs, have proven invaluable. These networks, particularly long short-term memory, LSTM models, are designed to handle sequences and capture long-term dependencies in data, which is essential for generating videos with temporal consistency. More recently, transformer models, known for their success in natural language processing, have been adapted for video generation. They use self-attention mechanisms to capture long-range temporal dependencies, which makes them ideal for generating coherent sequences in video content. These technologies are constantly being refined, and hybrid models that combine aspects of GANs, VAEs, and RNNs are increasingly being used to tackle more complex video generation tasks. Recent advancements in GAN-based video generation have focused on improving spatial and temporal coherence. One of the significant improvements has been the introduction of 3D GANs, which generate volumetric content, allowing for the creation of videos that are not limited to 2D representations. These models can generate dynamic 3D scenes where objects and environments interact in a realistic way. This allows for more complex simulations of moving objects, or realistic interactions between characters and their environments. A key challenge in video generation is ensuring that the motion between frames remains consistent, and 3D convolutions have been a significant development in addressing this issue. These convolutions extend traditional 2D convolutional layers to process not just the spatial information in each frame, but also the temporal continuity, enabling the generation of smooth motion across multiple frames. Another critical development is the use of perceptual loss functions, which measure how well the generated video aligns with human perceptual standards. By focusing on high-level features of the video rather than pixel-wise comparisons, perceptual loss improves the realism of generated videos, particularly when it comes to rendering complex scenes and interactions. Recurrent neural networks, RNNs, have played a pivotal role in video generation, especially when it comes to handling sequences of frames over time. Long short-term memory, LSTM networks, a type of RNN, are particularly well suited to this task. LSTMs are designed to remember information from previous frames and use that knowledge to generate the next frames in a video sequence. This ability to handle long-range dependencies allows LSTMs to generate smooth, consistent video content, even in more complex scenarios where multiple variables change over time. LSTMs are commonly used in video prediction tasks, where the model is trained to predict the next frames based on a sequence of previous frames. This approach can be used for video forecasting, such as predicting the future movements in sports, traffic patterns, or even human behavior in a video. However, training RNNs for video generation is notoriously difficult. One of the primary challenges is ensuring that the model remains stable across long sequences and does not produce erratic or unrealistic outputs as the sequence grows. To overcome these challenges, techniques such as gradient clipping, data augmentation, and careful initialization of weights are used to stabilize training. Transformers, originally designed for natural language processing tasks, have shown incredible promise in video generation due to their self-attention mechanisms. These mechanisms allow the model to weigh the importance of different frames or parts of the video, enabling it to capture long-range temporal dependencies that are difficult for traditional RNNs. Unlike RNNs, which process data sequentially, transformers can analyze all parts of the sequence simultaneously, making them highly efficient in modeling long-term relationships across a video. The self-attention mechanism allows transformers to better capture motion consistency across frames by considering the entire context of the video sequence rather than just local patterns. This makes them ideal for generating videos where the motion of objects, the flow of scenes, or the transitions between frames need to be smooth and coherent. However, one of the challenges of using transformers for video generation is their computational cost. The attention mechanism scales quadratically with the length of the input sequence, which makes processing long, high-resolution videos computationally expensive. Researchers are exploring sparse attention and hierarchical attention mechanisms to mitigate this issue and make transformer-based video generation more scalable. Video-to-video synthesis is an exciting application of AI, where the goal is to generate video sequences from single images or even rough sketches. Techniques such as Pix-to-Pix and cycle GAN, which were initially designed for image-to-image translation, have been adapted for video generation. These models work by learning the relationship between input and output domains, mapping static images to corresponding video sequences, or transforming sketches into realistic animations. One of the main challenges in video-to-video synthesis is ensuring temporal consistency between frames. Since videos consist of multiple frames that need to flow smoothly from one to the next, it's critical to maintain continuity, both in terms of motion and scene composition. Researchers have developed methods such as multi-frame training and temporal loss functions to address this issue. These approaches ensure that the generated video does not exhibit noticeable jumps or inconsistencies, allowing for more natural and coherent results. Video-to-video synthesis has vast potential in creative industries, including video editing, animation, and virtual content creation. Deepfakes, a term used to describe AI-generated videos that manipulate or replace people's faces or voices, have gained significant attention due to their potential for both creative applications and malicious uses. GANs are at the heart of deepfake technology, with the generator model creating synthetic faces or voices that are indistinguishable from real data, while the discriminator evaluates and refines these generated outputs. The technology has been used for various purposes, including in entertainment for creating realistic visual effects, but it has also raised serious concerns regarding its potential for misuse. The ethical issues surrounding deepfakes are profound, especially in the context of misinformation and privacy violations. Deepfakes can be used to create highly convincing fake videos, such as politicians making false statements, celebrities being portrayed in compromising situations, or individuals being impersonated. This poses significant risks to personal privacy and political stability. As a response, there has been a significant push in developing AI models designed to detect and mitigate deepfakes, such as using deep learning techniques to analyze inconsistencies in facial expressions, lighting, or pixel-level artifacts that reveal synthetic content. While these detection systems are improving, the arms race between deepfake creation and detection continues. AI-driven video generation has a wide array of applications across several industries. In the film and entertainment industry, AI is being used to assist in generating realistic visual effects, digital actors, and even entire movies. In particular, AI tools are being developed that allow filmmakers to quickly generate and edit complex scenes or create realistic simulations of environments. This has the potential to drastically reduce production costs and timelines, while also allowing for creative exploration that may not have been feasible before. Virtual and augmented reality, VR/AR, is another area where AI video generation is having a significant impact. AI is used to create immersive worlds and realistic environments that users can interact with in real time. This has important implications not only in gaming but also in fields like training, therapy, and education. Educational simulations in particular benefit from AI-generated video by enabling realistic, interactive learning experiences that can simulate complex situations, from medical procedures to industrial processes, without any risk. In video games, AI is enabling more dynamic and responsive environments where virtual characters can learn from player actions and adapt accordingly. AI-driven video generation is having a profound impact on the healthcare industry, particularly in training and patient education. One of the most valuable applications is in generating training simulations for healthcare professionals. By using AI to create virtual surgeries, diagnostic procedures, or other medical scenarios, healthcare workers can practice complex tasks in a safe, controlled environment without risk to patients. This also allows for the creation of highly customized training scenarios based on specific medical conditions or rare cases, something that would be difficult to replicate with traditional training methods. Moreover, AI-generated videos are increasingly used in patient education, where they can explain complex procedures, conditions, or treatments in a way that is both understandable and visually engaging. These videos can help patients better understand their diagnosis and treatment options, leading to better decision-making. Finally, AI is also being used for disease prediction and analysis, such as simulating the progression of certain conditions or predicting the outcomes of specific treatments. By visualizing these scenarios, medical professionals can gain deeper insights into patient care and treatment planning. With the rise of AI-generated videos comes a set of ethical challenges that must be addressed. One of the most pressing concerns is the potential for AI to be misused in creating misleading or harmful content. For instance, deepfake technology can be used to generate fake news, create misleading political statements, or damage an individual's reputation. The power of AI to manipulate media in such a realistic way raises serious concerns about misinformation and trust in the media. Another significant challenge revolves around intellectual property and ownership. If an AI generates a video, who owns the rights to that content? Is it the developer who created the AI model, the person who trained it, or the user who provides the input data? These questions are complicated and must be addressed as AI video generation becomes more prevalent. Furthermore, as the technology matures, there is an urgent need for regulation. There must be clear guidelines in place to ensure AI-generated videos are used ethically and responsibly, particularly in sensitive applications such as journalism, political media, and personal data protection. Looking to the future, there are several exciting directions in AI-driven video generation. One major challenge is scaling models to generate high-resolution videos without compromising quality or computational efficiency. Current video generation models struggle when faced with high-resolution content or long video sequences, as processing power increases exponentially with both resolution and video length. Overcoming this limitation will be crucial for real-time applications, such as video streaming or live event creation. Another area of focus is improving interactivity in AI-generated videos. In gaming, VR, and even educational environments, interactivity can enhance user experience by allowing users to influence or co-create videos in real time. This can involve generating personalized video content that adapts to individual user actions or decisions. Finally, we can expect AI models to continue evolving to support cross-domain applications. Integrating AI-generated video with other forms of data, such as audio or text, will allow for more seamless multimodal content creation. This means that the future of video generation could involve the creation of fully interactive and adaptive videos, where users can control not only what is seen, but also what is heard, creating richer and more immersive experiences. AI is beginning to transform the way films are made. In scriptwriting, AI is being used to assist writers by suggesting plot twists, dialogue, or character interactions based on certain inputs. AI-based tools are capable of analyzing vast amounts of existing scripts and coming up with new ideas that adhere to certain genres or styles, which can help speed up the scriptwriting process. In animation and character generation, AI is making real-time rendering and character design possible. Studios are now able to create entire animated sequences or render detailed characters using machine learning algorithms, dramatically reducing production times. Additionally, AI is being applied in video editing and post-production tasks. For example, AI can automatically trim excess footage, adjust color schemes, and even enhance visual effects. This type of assistance allows filmmakers to focus on the creative aspects of production rather than on repetitive tasks.
In virtual reality, VR and gaming, AI is playing a transformative role in how we experience and interact with virtual worlds. For VR games, AI is used to generate vast, immersive 3D environments that players can navigate in real time. These environments are often dynamic and interactive, with AI adjusting aspects of the world based on the player's actions. NPC behavior in games has also been enhanced through AI, allowing characters to react to players' decisions and interact in more natural and intelligent ways. For example, NPCs can learn and adapt to player strategies, making gameplay more challenging and engaging. Procedural generation is another key aspect of AI in gaming, allowing developers to create massive open-world environments that are generated on the fly based on algorithms. This reduces the amount of manual work required for game design and allows for more expansive, randomized worlds. Finally, AI is enabling adaptive storylines, where the narrative changes in response to players' choices. Instead of following a fixed path, the storyline evolves and adjusts based on user decisions, offering a more personalized and engaging experience. To conclude, the progress made in AI-driven video generation is immense, with far-reaching implications across multiple sectors. The ability to create realistic, coherent videos has already transformed industries such as entertainment, healthcare, education, and gaming. However, significant challenges remain, particularly around maintaining temporal consistency across video frames, scaling models for higher resolution, and addressing ethical concerns like deepfakes and content ownership. The future of video generation is incredibly exciting. We are already seeing a shift toward real-time video generation, interactive content, and highly personalized media experiences. As these technologies improve, we are likely to see even more groundbreaking applications, from AI-assisted filmmaking to virtual environments where users can control and personalize their experiences in entirely new ways. Video generation will continue to evolve, making it an exciting area of AI to watch closely.